For 40 years, battery engineers and the entire Western automotive industry told the world that liquid electrolyte was not a design choice. It was a thermodynamic necessity. That without an organic solvent medium, lithium-ion simply could not move fast enough to power a vehicle, charge a phone, or run a factory. That solid-state batteries were a laboratory curiosity, always 5 years away, never arriving. The constraint, they said, was not engineering. It was physics. It was permanent. CATL's argyrodite sulfide electrolyte, now matching liquid ionic conductivity at 10 millisiemens per centimeter, while operating stably at negative 40 degrees Celsius, just proved every word of it wrong. A 6C cell, 10 minutes to 80% charge, no liquid, no fire risk, no winter performance cliff, and a system-level energy density of 350 to 380 watt-hours per kilogram, 75 to 90% higher than every NMC liquid pack currently sold in an American showroom. This is not just a battery story. This is a Jeep story, a Toledo story, a 40-year supply chain story that the Western automotive industry is only now beginning to understand it has already lost. In 1991, Sony shipped the world's first commercial lithium-ion battery. It used liquid electrolyte, a mixture of organic carbonate solvents that allowed lithium ions to move freely between electrodes. The technology worked. Within a decade, it powered laptops. Within 2, it powered Tesla's first Roadster. Within 3, it became the unquestioned foundation of a global electric vehicle industry, worth trillions of dollars. Detroit did not ignore this transition. GM spent $35 billion on its Ultium platform. Ford committed billions more to Blue Oval. Stellantis launched the Wagoneer S, the Dodge Charger, Daytona, the Jeep Avenger. Every one of these vehicles runs on the same electrochemical architecture that Sony commercialized in 1991. The organic solvent, the liquid electrolyte, the compromise that the entire industry decided at some point between 2015 and 2020 was good enough to build the next 30 years on. What no one in Detroit asked, at least not loudly enough, was whether the material was actually optimal or simply familiar. Whether the industry had chosen liquid electrolyte because it was the best answer or because it was the first answer that worked at scale, and no one had yet built a production line around anything better. CATL asked that question. Not in a press release, not in a concept car, in a materials science laboratory between 2018 and 2024, with 200 patents and $15 billion in committed capital. The answer they found is arriving in limited production form in 2027, and Detroit will not have a production response until the decade is nearly over. The core problem with liquid electrolyte has never been energy density. It has been the solvent itself. Ethylene carbonate, the primary carrier in every NMC cell in every American EV showroom, has a flash point of 25 degrees Celsius, the same temperature as a warm afternoon in Phoenix. The organic solvent that powers a $60,000 American SUV is by definition flammable at room temperature. For 30 years, the industry managed this risk with battery management systems, thermal barriers, and passive fire suppression. Management, not elimination. CATL's sulfide electrolyte, specifically an argyrodite compound designated Li₆PS₅Cl, removes the solvent entirely. What replaces it is a ceramic material that conducts lithium ions through a solid crystal lattice rather than a liquid medium. The ionic conductivity of this compound has now been validated at 10 to 25 millisiemens per centimeter at room temperature. For reference, conventional liquid electrolyte conducts at approximately 10 millisiemens per centimeter. For the first time in the history of rechargeable batteries, a solid material matches the ion transport speed of a liquid without any organic solvent present. There is nothing to combust. There is no vapor to ignite. The fundamental fire architecture of the battery has been removed, not managed. In January 2026, a Jeep Wagoneer S owner in Minneapolis posted a single photograph to a forum. The car's range display read 178 miles. The outside temperature read -12 Fahrenheit. The car had left the dealer with a rated range of 303 miles. The post received 4,000 replies. Half of them said the owner was doing something wrong. The other half said they had the same experience. Neither half understood the chemistry. Ethylene carbonate, the primary solvent in the Wagoneer S's Samsung SDI cells, begins to solidify at approximately 36 degrees Celsius, meaning it is technically solid at room temperature. It must be blended with dimethyl carbonate to remain liquid. Below 0 Celsius, the blended solvent's viscosity rises sharply. Lithium-ion diffusion rates fall by roughly 50% for every 10 degrees Celsius drop in temperature. At -18 Celsius, the temperature of that Minneapolis morning, the Wagoneer S's cells were operating at a fraction of their designed ion transport capacity. The battery management system responded the only way it could. It restricted charge rate, restricted discharge rate, and reported a range of 178 miles. Not a software error, not a calibration issue, a chemistry problem that no firmware update can fix. CATL's sulfide solid electrolyte has no solvent to freeze, no viscosity to rise, and no diffusion coefficient that collapses under cold. Projected winter range loss for a sulfide ASSB vehicle at 0 degrees, Fahrenheit 5 to 8%. The Wagoneer S loses 38. That gap 30 percentage points is not a feature difference. It is an architectural difference. And it exists in the single largest geographic market for truck and SUV sales in the world, the American Midwest and Mountain West, where January temperatures routinely reach the range at which liquid electrolyte chemistry begins to fail. The Jeep Wagoneer S charges at a maximum of 150 kilowatts. That is not a hardware limitation. The cables can carry more. The inverter can process more. The limit is the chemistry inside the cell. When you push a liquid electrolyte NMC cell above approximately 2 to 3 C rate, meaning charging at 2 to 3 times its rated capacity per hour, lithium ions begin arriving at the graphite anode faster than they can be absorbed. The excess lithium deposits on the anode surface as metallic lithium. These deposits grow into needle-like structures called dendrites. Dendrites can penetrate the separator between anode and cathode. When they do, the cell short circuits. At high states of charge, a short circuit in an NMC liquid cell is not a contained event. This is why the Wagoneer S charges at 150 kilowatts, not 500. Not because Stellantis didn't want to offer faster charging, because the solvent-based chemistry imposes a hard ceiling on how fast ions can safely be forced through a liquid medium without triggering the exact failure sequence that ends with a burning SUV on the side of a highway. CATL's sulfide solid electrolyte eliminates the dendrite pathway entirely. The solid ceramic matrix under 5 to 10 megapascals of mechanical stack pressure physically constrains lithium-ion deposition. There is no liquid medium for dendrites to grow through. The theoretical charge ceiling for a sulfide ASSB cell is not 1.8 C. It is 6 C, 10 minutes to 80%. Not as a marketing claim, as a consequence of removing the material that imposed the limit in the first place. This is the point at which solid-state battery discussions in the Western press typically end. The technology sounds impressive, the argument goes, but solid-state has been 5 years away for 20 years. QuantumScape went public in 2020 with promises of vehicle cells by 2024. Solid Power raised $250 million with Ford and BMW as backers. Neither has shipped a production cell. The pattern is familiar. Extraordinary claims, extraordinary funding, and then silence. CATL is not a startup. It is the largest battery manufacturer in the world, supplying cells to Tesla, BMW, Toyota, Volkswagen, and Hyundai simultaneously. It produced 390 gigawatt-hours of cells in 2024 alone. When CATL CEO Robin Zeng stated publicly in December 2024 that the company would have all solid-state cells in limited production. By 2027, He was not making a venture capital pitch. He was announcing a manufacturing decision that had already been funded, staffed, and scheduled. The difference between CATL's 2027 commitment and QuantumScape's 2020 promises is not optimism. It is the difference between a company that has never built a production battery line and a company that builds the equivalent of a new gigafactory every 18 months. The cells are not ready for mass market today. They will not be in every vehicle by 2030, but they will exist in limited production volume before any American manufacturer has a credible response. And in the battery industry, the company that achieves limited production first controls the cost curve, the patent position, and the supply chain relationships for the decade that follows. The Jeep Wagoneer S deserves to be taken seriously before it is taken apart. It is, by any objective measure, a well-engineered vehicle. The Samsung SDI Gen 5 NMC811 cells it carries represent some of the highest energy density available in a production prismatic format, 280 watt-hours per kilogram at the cell level. The 83.6 kilowatt-hour usable pack delivers a genuine 303 miles of EPA range. The interior quality matches vehicles costing $30,000 more. The Toledo assembly complex, where it is built, employs over 6,000 UAW workers. This is not a compromised product. It is the best that liquid NMC architecture can currently offer, at this price point, assembled by American workers in an American factory. The problem is not what the Wagoneer S is. The problem is what it is built on. At $72,500, a buyer is purchasing a vehicle whose core energy storage architecture, liquid organic solvent electrolyte, NMC811, cathode chemistry. Graphite anode was commercialized in 1991 and has not undergone a phase state change since. They are purchasing a vehicle that will lose 38% of its rated range when driven in Minneapolis in January. They are purchasing a vehicle that requires 35 minutes to charge from 20 to 80% at the fastest available DC station. And they are purchasing a vehicle whose battery degradation is governed by the same dendrite formation and electrolyte decomposition mechanisms that have limited liquid lithium-ion cycle life to 1,200 to 1,500 cycles since the technology's inception. Against CATL's 2027 target specifications, the gap is not incremental. A Sulfide ASSB vehicle built on equivalent pack volume would deliver an estimated 450 or more miles of EPA range in summer conditions. At 0 degrees Fahrenheit, that same vehicle would lose 5 to 8%, arriving at roughly 420 miles of winter range, versus the Wagoneer S's 185. The charge time drops from 35 minutes to approximately 10. Cycle life extends from 1,200 cycles to 3,000 or more. Stellantis understands this. The company invested $75 million in Factorial Energy, an American ASSB startup, as early as 2021. But Factorial uses an oxide-based solid electrolyte, not sulfide. Oxide electrolytes have lower ionic conductivity than sulfide at room temperature, require higher interface resistance management, and have proven significantly more difficult to manufacture at scale. As of mid-2026, Factorial remains in pilot production. The gap between Stellantis' ASSB investment and CATL's ASSB production timeline is not a gap in ambition. It is a gap in chemistry selection and manufacturing commitment, and it is measured in years, not months. The Wagoneer S will still be on sale when CATL's first solid-state cells enter limited production. The question its buyers should be asking is not whether the car they are purchasing today is good. It is whether the architecture it runs on will still be competitive in the second half of its ownership life cycle. The battery transition that CATL is engineering is not a product launch. It is a supply chain reorganization, and the United States is not positioned to participate in it on competitive terms. Sulfide all-solid-state batteries require a fundamentally different set of raw materials than liquid NMC cells. The sulfide electrolyte synthesis process begins with lithium sulfide and phosphorus pentasulfide compounds that China currently processes at over 80% of global capacity. The United States has no commercial-scale sulfide electrolyte manufacturing. It has no announced federal program to build one. The $3 billion in battery manufacturing grants allocated under the Inflation Reduction Act targets liquid NMC cell production facilities operated by LG Energy Solution in Holland, Michigan, Samsung SDI in Kokomo, Indiana, and Panasonic in DeSoto, Kansas. Every dollar of that federal commitment is being deployed into an architecture that CATL has already decided to move beyond. The workers are not invisible in this calculation. The Toledo assembly complex, where the Wagoneer S is built, employs more than 6,000 UAW members. Their jobs depend on Stellantis' ability to fund a chemistry transition, not a model refresh, not a new color option, but a complete reconstitution of the electrochemical architecture inside every vehicle on that line. Stellantis entered 2026 with $5.5 billion in restructuring costs, a vacant CEO position, and 11 North American manufacturing facilities under strategic review. The capital required to pivot from oxide ASSB partnership investment to sulfide ASSB production capability does not exist in the current Stellantis balance sheet. Tariffs do not change this equation. A 100% import duty on Chinese electric vehicles prevents a BYD sedan from entering an American showroom. It does not prevent CATL from licensing sulfide electrolyte production technology to a facility in Mexico, achieving USMCA compliance and supplying cells to any automaker willing to pay for the chemistry advantage. The technology transfers. The trade restriction does not follow it across the border. What happens next depends not on tariffs, but on whether American industrial policy can distinguish between protecting existing liquid NMC infrastructure and building the sulfide ASSB capability that will define the next 20 years of battery competition. The liquid electrolyte battery is not ending because China built a better product. It is ending because China solved a material science problem that the Western industry spent 40 years insisting was permanently unsolvable and committed $15 billion to production infrastructure before the Western press had finished writing articles about why solid-state batteries would never work. Somewhere in Toledo, Ohio, a UAW worker is installing Samsung SDI-NMC811 cells into a Jeep Wagoneer S today. The organic carbonate solvent inside those cells flashes at 25 degrees Celsius. It loses 38% of its energy at 0 degrees Fahrenheit. It forms dendrites above 2C charging. It has done all of these things since 1991. In 2027, CATL will ship its first limited batch of cells that do none of them. In 2030, those cells will enter mass production. The chemistry that Worker is installing today will not receive a software update that fixes its fundamental limitations. It will not be patched. It will be replaced either by an American manufacturer that finds the capital, the chemistry expertise, and the policy support to compete, or by a supply chain that has already spent a decade building exactly that capability. While American industrial policy was funding the architecture, it was designed to supersede. The question is not whether solid-state batteries work. CATL's production timeline answers that. The question is whether Stellantis, GM, and Ford can execute a chemistry transition, not a platform refresh, not a new model year, while simultaneously managing billions in restructuring costs, defending profitable truck lines from tariff-driven disruption, and retraining a workforce built around a technology that is now entering its final decade of dominance. That answer will not come from an earnings call. It will not come from a government press release about battery grants. It will come from a production line, And right now, only one side of this competition has one scheduled.